We're going to do problem 2930, 2930, 293, 0. Number of strings which can be rearranged to contain substrings. Now, forewarning, this really isn't a standard data structures and algorithms problem, right? This is one of those kind of strange outlier Leetcode problems that have very little to do with data structure and algorithms, right? Some high percentage, probably 95 to 99% of the problems you see on Leetcode, the kind of problems that you're going to get within an interview for a software engineering role or something similar, are going to be standard DSA, right? Standard data structures and algorithm type problems, right? You're going to be using trees, you're going to do some graph stuff, you're going to do DFS, you're going to do BFS, you're going to do uniform class search, you're going to do union, quick find, you're going to do something, dynamic programming, whatever, right? But sometimes there's problems where even though you may be able to use data structure and algorithms to solve them, the optimal solution actually uses some, sort of related but separate topic. And the separate topic is definitely what's occurring here. And that topic is stats. Okay, so the optimal solution to the problem that we're about to do today is just a standard kind of intermediate to advanced statistics problem. It isn't really so much, your standard. It really isn't a data structures and algorithms question. So it can be kind of frustrating when you encounter problems like these because the interviewer say, oh, that's not the optimal solution. And then the interviewer might hint to you, oh, the optimal solution uses statistics. It's like, well, I'm not a statistician. I'm not a mathematician. I'm an engineer, right? And if I'm a software engineer, I'm dealing with this over here. All right, I'm dealing with data structure and algorithms, not statistics. So why are you asking me a statistics problem? So with all that said, let's go ahead and get right into it. But just understand that today, I'm really going to be solving a statistics problem more so than I'm going to be solving a programming problem. And then I'm going to do simple calculations and return, the answer. So what does that mean within the context of this problem? Okay, so you're given an integer n, all right, simple enough. And a string s is called good. Why are we talking about s of n? Whatever. It's called good if it contains only lowercase English characters, and it is possible to rearrange the characters of s such that the new string contains leet as a substring. Okay, so it's good if it contains lowercase English letters. Okay, so what does that mean in terms of what you can have? Well, you can have all the lowercase English letters. So what are those? Those are A through Z. So A, B, C, all the way to Z. And how many of those are there? Where there's 26, right? Probably something you should have memorized if you're solving problems like these, right? There's 26 lowercase English letters, A through Z. I don't know what language you speak out there in the universe, wherever you're watching. Maybe you speak Klingon. I don't know. But whatever you speak, in English, there's 26 lowercase letters. It's a very... we're not going to talk about linguistics today. Okay, and it's possible to rearrange the characters of S such that the new string contains leet as a substring. Okay, so let's look at some examples and see if it's a good substring meeting these criteria. The first one they give is L, T, E-E-R, right? Now, something being a substring means what exactly again? That means if you have a string like this, right, A, B, C, D, leet, F, E, G, right, you can draw a box around the thing that you're looking for, right? So leet is a substring, right? Because I can draw a box around it without like skipping characters, right? ABC is a substring. It's a substring of the longer string, right? It's a sub part of it, right? But LTF is not a substring, right? Because in order to get LTF, I have to like do that, right? Because I have to skip those two E's here. So substring is going to draw a box, right? It's continuous characters within a string. Okay. Now you might be looking at this and say, well, leet isn't a substring, right? Because you'd have to like there's L, but then you'd have to go around the E somehow and then get the T. I don't know, right? But the thing is you can rearrange the characters of S, right? So I can take this and move the T over here, right? Swap it with E, swap the E with E, whatever I have to do. Rearrange the characters, and then voila, there you go. There's that leet we were looking for, right? So LTER, even though it's not immediately noticeable, with some rearrangement, it is good, right? Now, on the other hand, what if I had L? What if I had A, L, E, E, T? You might say, oh, well, I have leet here, right? But remember, I'm just trying to make the point here where they can only have lowercase English letters, right? So that's the only thing we need to think about. We're not going to think about this uppercase A. This causes a problem, so we eliminate this. Even though it has leet, right? There's really two conditions, right? There has to be only lowercase English letters and leet as a substring rearranged, right? Or not arranged. Maybe there's already a leet in there. All right, and then the final example here, we have L-E-T-L. So it's all lowercase, so that's good. But you'll notice that there's no way to rearrange this to make this work, right? Because we are missing an E. Okay? And that's kind of the first thing to think about in terms of the conditions of this problem, right? To be good, it has to have leet and it could be rearranged. So if I can rearrange the characters, it doesn't matter the order of the characters. I just need to have all the characters within the string. And what I mean by that is, here's an extreme example, right? The most extreme example, I guess, of something being rearranged, maybe, would be T-E-E-L. Right? As long as I have a T, two E's, and an L, I can recreate the string, right? Because I can move the L over here and these two E's and this T. Right? It doesn't matter how I do this, but as long as I have as long as I have two E's, an L, and a T, I can make this work. Right? So a string is good. Another way of stating this, right? So we're going to restate this in a way that can be used in our little statistics calculation, right? Just from this kind of observation from this, really, right? Is that in order for it to be good, all we need is what? We need, where am I going to put this? Only lowercase. And we need what? We need at least one L. So I'm going to put greater than or equal to one L. We need at least one T. And we need at least two E's. I'll draw my T like this so you can tell it's a T and not a plus. Okay? So that's all we need for this to work, right? If we have this condition and this condition, it works. Because even if the L and the E's and the T's aren't in the right order, well, we can rearrange. So as long as we got the ingredients we need, we can reorder that baby and make it A-okay. And by the way, this is not soda. Quit drinking soda. This is seltzer, which is just like a transitionary thing to water, right? If you're drinking soda every day, like if you're drinking alcohol every day, maybe switch out the alcohol for soda. And if you're drinking soda every day, maybe switch the soda out for seltzer. And if you're drinking seltzer every day, right, which is bubbly water, carbonated water, then swap to water, right? But it's a transitionary period. Yeah? You got to crawl before you walk, and walk before you run, and run before you fly, and fly before you die. I don't know. Anyways, so these are the conditions you need in order to get a good string. So how many good strings can you create in a certain situation? Well, as long as you can create all the lowercase and have at least one L and at least one T and at least two T and at least two E's, you can make it work because you can just rearrange things, right? Because in this problem, I have one L, one T, and two E's. Doesn't matter the order. I'll just rearrange them to make it leet, and that'll be a good substring. Right? And this one doesn't work even though I have all the things I need. It has to be only lowercase, so this A is a problem. Okay, so we want to return the total number of good strings of length n. Since the answer may be large, return it modulo 10 to the 9 plus 7. Okay, so for n equals 4, I'm not going to go through it, right? We have 12, right? Because, well, we could have, well, basically, for 4 things, right? If we only have 4 spots, let's think about it like this, right? Now, here's where it becomes very statistics-like, right? If you've taken a stats class or, you know, discrete math or whatever, you've probably been in a situation like this where you say, okay, I have an L, an E, and an E, and a T. I need that at least, and it can only be lowercase, so I only have spaces for, you know, the L, the E, and the T, and I can do any order of that, right? So I have 12 possible ways I could do it, right? I could do it like this and rearrange, like this and rearrange, like this and rearrange, like this and rearrange, and so on and so forth. N equals 10, there's a lot, and it's also modded by 10 to the 9, 7, so this blows up pretty quick, right? But how do we go ahead and solve this? Well, let's think about how this would work, okay? So we know for sure we need these things, right? We need one L, we need one T, and we need one E, okay? So, you know, if we don't have any of these one things, it's an issue, right? If I have all lowercase and I have an E and an E and a T and an F and a G, or a lowercase f and a G and an H and an E and a T, this doesn't work. Why? Because I need all these conditions to be true, right? So if any of one of these conditions are not true, it doesn't work, right? So I can have all the strings except for these ones where these things aren't true. So if I have an L where I have less than one, if I have less than one L, right, the opposite of these things. If I have less than one L, I can't make this work, right? For example, if I had EETX. If I have less than one T, I can never make it work, right? What if I had EELX? And if I have less than two T's, two E's, I can't make this work, right? If I have ELTX. Right, so if any of one of those conditions don't work, this won't happen, right? So everything will work except for situations where either I have less than one L or less than one T or less than two E. And this is the same thing as saying 0 L's. This is the same thing as saying 0 T's. And I'll leave this as less than 2 E's. Just for the sake of simplicity, right? Because less than 1 L, well, the only thing that's less than 1 is 0, I guess. I mean, there's negative numbers, but you can't have negative number of E's. It doesn't make sense, right? So we don't have to consider that angle. But, you know, if I have less than 1 L, that means the only option I have is 0 L's, right? So if I have 0 L's, 0 T's, or less than 2 E's, this is a problem, right? So those are the conditions of which this is going to be an issue, okay? So where do we go from here? Well, that's kind of an observation, right? Just knowing like, well, I can do everything except for any of these cases, right? So how many things can I really do? So let's just look at an example like n equals 5, okay? So let's just say, for example, we're looking at n equals 5. So that means I have 5 places where I can put things, right? Now, how many things can I put in each slot? Well, remember, there's 26 characters. So what I mean by that is, well, I could put 26 things here, right? Because I could put A, B, C, all the way down. I could put 26 things here, 26 things here, 26 things here, 26 things here. So for n equals 5, I can do, there's 26 to the 5 possible combinations of things that I can do. Not combinations, whatever. But there's 26 to the 5 possibilities in terms of the strings that I can create, right? Because if these are all A, B, C, D, how you see how this works, right, is I could choose A here, and then B here, and then C here, and A here, and B here, right? Or whatever, right? So I could get a string, for example, like that, right? So there's 26 of the 5 possible combinations. All of those work except for the cases where I have less than 1 L. When I have less than, if I have 0 L's, 0 T's, and less than 2 E's, right? So all of the cases work except for the ones like this, right? Every string in this path, right? All these 26 to the 5 strings work except for the cases where it doesn't have at least 1 L, it doesn't have at least 1 T, and it doesn't have at least 2 E's, right? Because, for example, this is one of those bad ones, right? This string is bad because it doesn't have one of these conditions. It could have more than one of the conditions, but it definitely doesn't have at least one of them, so this string would be subtracted, right? So basically what I'm doing is I'm saying my solutions are everything that I could have minus everything that would cause a trouble, right? So this is everything that I could have, right? 26 to the 5, or generally 26 to the n, minus everything that would create an issue, right? All the situations where I don't have an L, and I don't have a T, and I don't have 2 E's, okay? So that's one way of thinking about this, right? That's a very standard statistics way of thinking, right? Saying like, my answer is everything I can have minus everything possible. My answer is everything that's possible minus the things that won't work, right? That's what I can have, right? So, and maybe that you should take a moment to think about that, but, you know, that's the general idea of this problem, right? It's saying, well, you know, everything will work except for the cases where I don't have an L, I don't have a T, and I don't have two E's. Okay. So where do we go from there? Well, let's think about those cases case by case, right? So what would it mean if you didn't have an L? Because we want to subtract out those cases, right? We want to subtract out the cases where we don't have the character that we need. So, you know, for example, for n equals 5, what would it mean to not have an L? So what would it mean to have 0 L's? Well, to have 0 L's, that means that none of the characters can be L, right? There's 0 L's, so none of the characters can be L. So we can put anything in this slot except for L. Right, so I can put anything in this slot except for L. And that's the truth for all the slots, right? So that means I have, how many things can I put in the slot? I can put 25 in this slot, 25 in this slot, 25 in this slot, 25 in this slot, 25 in this slot. So having 0 L's equates to 25 to the n possible ways, right? There's 25 to the n possible ways of creating a string that has 0 L's, right? Because that means in each slot, I didn't choose an L, okay? So it's 26 total options, but I can't use an L, so that option gets removed. All right. How about having 0 T's? Well, to have 0 T's, it's the same thing, right? Just now I can't select T from the problem, right? So again, I have 25 things that I can do. And that equals 25 to the n as well. And then what about 0 or less than 2 E's? Well, less than 2 E's is, there's two things, right? Less than 2 E's can mean I have 1 E or 0 E. Right, so it's the combination of both of those, right? And those are exclusive events. I either have 1 E or 0 E. What's the sum of those? Well, let's do 0 E first because it's a little bit easier to grasp. So how many ways can I have 0 E's? It's the same thing, right? It means that I'm doing 25, 25, 25, 25, 25. So that equals 25 to the n. Right? Because you multiply them together. I can do anything but E. Here I can do anything but T. Here I can do anything but L. And then how many ways can I do 1E? Well, for 1E, the way I like to imagine is, well, let's look for 5, right? If there's 1E, the first thing could be an E, and the rest of them are 25. Or maybe the second thing is an E, and the rest of them are 25. Or I'm going to do all of it because it's just to make the point clear. The third thing's an E, the fourth thing's an E, the fifth thing's an E, and the other ones are 25. I'm trying to go fast here, guys. Sorry. All right, this is all the ways that it works. Right? So this is the first way it could happen, which is 25 to the 4th power, right? Because what happens is I use one of the n slots, right? I use one of the n slots for the E, and the rest of them are the 25 remaining characters that I can use, right? So these are all the cases where there's one E. There's an E here and anything else over here. There's an E here and there's anything else over here. There's an E here and there's anything else over there, right? So this would be 25 to the n minus 1, right? Because there's 25 to the n minus 1 remaining spots where I can put anything I want, and there's one slot where I have an E. So there's 25 to there's n spots, but now there's only n minus 1 spots where I can put 25 things because I'm excluding E, right? But I could do that how many times? Well, there's 25 to the n minus 1 here and going down. So there's n ways. So there's n places I can put the E, and in the n places that I put the E, there's 25 to the n minus 1 possible additional things that I can do. So this basically sums up to n times 25 to the n minus 1. Okay, so that means less than 2E equals the sum of these two things, right? So that equals 25 to the n plus n times 25 to the n minus 1. You could do some factoring, I guess. I'm not going to do all that. But yeah, that's the right here. 25 to the n plus n times 25 to the n minus 1. Okay, so that's less than 2E. So you might feel inclined to say, okay, well, my answer is these cases, right? There's the case where, so I have all the things that I can do, minus the case where I have 0 L's, which is 25 to the n, minus the case where I have 0 T's, which is, there's 25 to the n of that, and minus the case where I have 2e, which is 25 to the n plus n times 25 to the n minus 1. Now I'm just writing this small because it doesn't really matter. Now, although these events are correct, this is where statistics, I mean, if this isn't already hard enough, this is where statistics gets a little cumbersome, right? It gets a little complicado. Un poquito complicado esta tatita, güey. This is where statistics can get complicated because, you know, these events aren't exclusive. And what I mean by that is, well, although there's 25 to the n cases where there's 0 L's, there's also cases where there's 0 L's and 0 T's. So we're kind of like over counting here, right? Because although there's 25 to the n cases where 0 L's and 25 to the n cases where there's 0 T's, these cases can share. Do you know what I mean? They can share events, so I'm going to overcount, right? I could subtract the same thing twice because I'm subtracting the cases where there's 0 L's and I'm subtracting the case where there's 0 T's, but these aren't exclusive cases, so I might overcount the same event, right? For example, I'm trying to remove all the strings where there's 0 L's. So one of those strings would be A, right? That definitely doesn't work in our answer, so we want to remove that, right? We have all 26 to the n possible combinations, all the possible ways we can do this, so we want to remove A from that answer. So that would get captured in this 25 to the n, and there's 0 L, so that meets the condition, so it would be within this 25 to the n. But 0 to the t also has 0 t's, right? And it meets this condition. So now I'm going to subtract it here and subtract it here. So I'm subtracting the same thing twice. So I'm over subtracting, right? So one of the main problems in statistics always is, how do you handle repeats? These damn repeats, they always mess you up, okay? Because these events aren't exclusive. So we have to think about this in terms of, well, you know, although there's 25 to the n's where there's 0 L's and 25 to the n there's 0 T's, and same with these e's, right? 0 e's, well, I could put all A here, and that meets these conditions. There's intersections, and we don't want to overcount them. So how do you deal with that in statistics, where you think about what we really want, right, is we want A, we want the case where there's 0 L's. Now this is the symbol for or. We want the case where there's 0 T's, right? Because we're trying to subtract those out. And we want the case where there's less than 2 E's. Okay? Now let's think about this in a diagram to figure out what this actually is, right? Because the problem is that there's intersection between these things. So we can't treat them as exclusive things because there's intersection between these things. So then we're going to end up over subtracting because we count this string multiple times because it meets this condition. But, you know, we got to think about, right? Because what we really want is, let's think about 3 big circles. Okay, so let's color code this. Oh. It's going to be really good. Just give me 1 second, guys. I apologize. Just want to make this perfect because this is going to be a pretty ugly drawing here. All right. So let's think of the amounts, right? The space kind of geometrically, right? So there's L, there's T, and there's E, right? Now what we want is we want L, and we want the cases where it's L, and we want the cases where there's T, and we want the cases where there's E. But the problem is like this example here with the A's, right? Is the intersection. And what that intersection really is like these areas here, right? There's L alone, right? But L has intersections with E, right? There's cases where there's 0 L's and there's 0 T's, right? That would be this area here, right? This area is where there's 0 L's and there's 0 T's. So how do we figure out what this is, right? Because what I want is the sum of all these things together, right? So what I might first say is, well, I want L. So I'll take all of L. Why is that so dark? Let's make this lighter. Okay. So I want all of L here, right? This blue circle. Because I want L and I want T and I want E. I want those things together. I want all three of those cases, but I don't want to overcount these areas where they share, right? So this L or U or E, right, is L by itself, right? And now maybe I want to grab the green area, right? So I might feel pressure to get the green area. But see what happens here, the problem is when I color all of the green, you notice how I'm over coloring again, right? So I'm adding this like kind of centerpiece twice. So in order to negate that as well, I want to get all of L. I want to get all of T, but I need to subtract out the area that's shared between L and T, right? Because I want to get L, but I want to subtract out this little sliver here. And this sliver here is the intersection between L and T, right? So I want to get all of L, but I need to subtract out the area where L and, now that's the symbol for and, T are shared, okay? Now the only area left I need to add is this area here, right? So I don't want to grab, again, it's the same kind of problem here. I could grab all of, and I still, okay, so, almost forgot, right? So I want T, but I need to subtract out this area, right? Because I don't want to add it again. So I get T. It's crazy how bad I am at this, man. All right. Oh my gosh. So I do want T, but I got to subtract the area where they are together. All right, now I want red, so I can't grab the whole area, right? Because this would be the whole area. But that would mean that I'm overcounting like this area and this area and this area. So I still want the whole thing, but I'm going to need to subtract out some things to make this work, right? So I'm still going to add in my E less than 2, but I need to subtract out a couple things, right? So first, I can subtract out the intersection between this thing and this thing, right? So basically, I color this whole thing. Right? But then if I subtract out the intersection between blue and red, so that would be LO and E less than 2. Right, so I'm basically subtracting that out, and I'm screwing up. Apparently you can't, you get the gist of what's happening here, right? I'm just going to recolor this really quick, but no, understand what's going on. Okay, so I color that out, but now I have this area that's empty, right? And I don't really know what this is, because this is like this thing and this thing minus this thing, I guess. But what I could do is I could just subtract out the red and the green together. So that would be TO and E less than 2. But then that's going to subtract out this area too, right? It's going to subtract out all of this, right? It's going to get rid of this area, but it's also going to get rid of this area, right? So what you'll end up having is this area will be cleared out now, because I've now subtracted this area twice, right? But as well as this area, not this whole area. Ugh. So this will be painted still. Right after you do that operation, it looks like this in terms of what you have painted. Actually, this would stay green because that's how it was colored originally. Right? So now we need to just add back in this center area, because basically we subtracted this sliver and then this sliver, right? We added to the sliver once with blue, but then we subtracted it from here and subtracted from here again. So now it's kind of empty. So if we add it back in, that would be the intersection of all three things. So that's the intersect. Where does the blue, the green, and the red intersect? And E less than 2, and T 0. And that would, I guess it would get a unique color because it's kind of the combination of all three. And you'll notice now that everything's only colored once, right? Because we want all these spaces. So it's kind of this tricky game of getting the intersection, right? And again, the intersection is where these strings are the same, like for example, AA, right? Because where there's 0 L's and 0 T's, they can share space. So this is over counting. So we need to subtract out the cases where they share so we get just this unique thing here. All right, so our final answer would be all the possible things we could get minus this bad boy right here. Okay, so some of these things we've already calculated, okay, up here. Did I forget to add in? I still need to add in this, the T0, right? Because I want this whole thing minus the parts. I want this whole thing minus the parts, this whole thing minus the parts. So some of these things we already have calculated, right? I already calculated what 0L is and what 0T is and what 2E is, right? So E less than 2, we calculated that was 25 to the n plus n times 25 to the n minus 1, right? Oh, I did put T0 there. My bad. T0 is up here. We decided that this was, why do I keep saying decided? We know it is, right? This is 25 to the n, and this is 25 to the n. So we need to determine what the rest of these things are. And then we'll have our answer. Right? We'll just do 26 to the n minus whatever these things are here. Okay, so what is L0 and T0? So what that basically means is, let's use the case of 5 again. You have 0 L's and you have 0 T's. Well, if you have 0 L's and 0 T's, that means you have 26 characters. You can't use an L and you can't use a T, so you have 24 remaining, right? So I can put any 24 characters in any of these slots except for... I can put any 26 characters except L and except T, so that means I have 24 total characters that I can use. So that is 24 to the n. All right, so this gets replaced with 24 to the n. Now this E less than 2 thing's a little bit tricky, right? Because, so what's L0 and E less than 2? Well, that's the same thing as, you know, L0 and E is 1 plus L0 and E is 0, right? Because it's exclusive, right? There's no intersection between E1 and E0. Either there's one E or there's 0 E. All right, so let's do L0 and E0. This is pretty simple. Like, this is just 24 to the n again, right? Because I can't have... maybe I'll just do it. Sorry. Right, but this is basically the same thing as before, right? Because... well, I can't have... I can't have what? I can't have an L and I can't have an E in any position. So this can't be an L or an E. 1, 2, 3, 4, 5. So that means there's 24 things here, 24 things here, 24 things here, 24 things here, 24 things here. So that's 24 to the n. Okay. So that's what this is, 24 to the n. What about L0 and E to the 1? So remember before when we did this with 5, right? I can put E in any spot, and then before I could put 25 things in the other spot. But now that I can have 0 L's as well, that means there's 24 things that I can put in each slot. Right? Because I can put E in one slot, and there can be no more E's. So that means in here there can be no E, so that's 25, and now also no L, so that means 24. So, and I can put E in any slot. So I can put E here, and the rest of these have to be 24. I put E here, and the rest of these have to be 24. So there's n ways, right? Because there's n places I can put E. And then there's 24 options, because I can't use an E in the remaining options, and I can't use the L. And there's n minus 1 remaining slots to do that. So then this is n times 24 to the n minus 1. So that means we know what this is now. This is, already forgot. 24 to the n plus n times 24 to the n minus 1. Now, I'm not going to go through T and E because it's the same thing, right? It's the same exact thing because, you know, here I can't have an L And then I have 24 options, and then 24 minus 1. Here I can't have a T, but it's the same exact kind of problem, right? I'm just exchanging the L for T. It's just another letter that I can't have. That's not E. So this would also be 24 to the n times n time. Wait, this is plus. 24 to the n plus n times 24 to the n minus 1. All right, so then I guess the only one we need to find out is this central piece, right? So that would be the case where we are in a situation where I have to check my phone. Whatever. Okay, so what does this look like? Now, see, there's no programming here. I'm just literally doing a kind of hard stats problem. So this would be the same thing as saying the case where there's one E and a case where there's 0 E's. And that's literally it. All right, so add those together. So if there's 0 E's, so this case is like, okay, I have, probably at this point you guys are getting where this is going, right? Let's do the 5 case again. 1, 2, 3, 4, 5. I can't have I can't have an E, I can't have an L, and I can't have a T. So that's 3 things I can't have. So I can use all 26 characters except those 3, so I have 23 options. So this would be 23 to the n. So this is 23 to the n. Now here there's, again, I'm not going to do it because it's literally the same thing. So it's n. I have n places I can put the 1E, and then I can't use the remaining, I can't put another E because I can only have 1. I can't use an L, and I can't use an E. So that's 23 to the n minus 1 because there's n slots where I put the E initially. All right, so this is what I keep forgetting. 23 to the n plus n times 23 to the n minus 1. All right, so there you go. That is your whole rabba-dabba-dooba. Okay, so that's your answer to this, right? So it's 26 to the n, all the possible things you can get, minus this whole junk. All right. So let's go ahead and just churn out the code now. That's all this comes down to, okay? So I'm going to use pretty ugly stuff here. So our final answer at the end, right, would be just return. I'm going to unplug my thing, and I'm just going to read it. Okay. So we're going to return 26 to the n minus the intersection of these things, right? And then we're going to have to mod that by 10 to the 9 plus 7. Okay, now we got to think about how we're going to get all these things. So we said that L0 was 25 to the n. We said that E0 was 25 to the n, right? Because we have n slots and we can't use one character. And T0 is 25 to the n. We said E1 is, well, I have n places I can put one E, and then there's 25 places where, there's 25 remaining characters I can use in n minus 1 slots. E2 is just the sum of E0 and E1. Now we got to do the combinations things, right? So L0 and T0 equals, well, now there's 24 things that I can use, right? Because I can't use one E, and I can't use a T, and I can't use an L. And there's n places I can do it. And then L0 and E2 is, well, I already did it. I'm not going to tell you guys what it is. I'm just going to tell you what it is. I'm reading right off here. All right, that's 24 to the n plus n times 24 to the n minus 1. T0 E2, just the same exact thing. And then the combination of those things is L0 T0 E2. Now these I'm just churning out numbers here. This is not pretty. I don't know how an interviewer would probably look at this by like, what the hell are you doing? But this problem isn't even a coding problem. I'm literally just doing calculations and I'm returning the answer. All right, is 23 to the n plus n times 23 to the n minus 1. And remember we said the sum of this was, well, we had all the elements individually, right? A and E and T. And then we got to start subtracting out the intersections, right? So we had to subtract out the intersection between L and T. We had to subtract out the intersection between L and E. And we had to subtract out the intersection between T and O. But then we had to add back in the intersection because we've overcounted. See, what in this tells you data structure and algorithm? Nothing. This is literally just churning out numbers based on a statistic problem. Look at all the times I got this wrong. This problem was not easy because I hate statistics. And I was trying to do... Don't get me started on what I was trying to do. So what's the runtime of this? Well, 25 to the n is log n, right? Because you have log n operations. So we're just going to call this log n. I'm done. So if you know the proper runtime here, it's definitely... I mean, is it... It's always weird when you do calculations because I'm doing calculations with respect to n, right? So the largest number I could have is n bits, so I'm doing log n operations in order to do these calculations. Okay. And then space, I guess log n, to generate these numbers, it's log n space. But someone might say this is constant. It depends on how you look at it. Okay. Peace out, guys.